Hello. I apologize. I tried to record this material in class and it didn't save, evidently. So what I thought I would do here is try to summarize what we did on Fridays or during Friday's class, and then I will also post my recording of Monday's class as well. So the starting point for last Friday were the first two of Newton's three laws of motion. The first law says what happens if there's no net force acting on an object. So that means there's no total aggregate push or pull. And you can really just say it as, if there's no net force, then the velocity remains constant. In particular, that means that if the object starts at rest, it stays at rest. If it starts out moving, then it continues moving in a straight line with a constant speed, which would be a constant velocity. On top of that, we have Newton's second law, which describes what a net force does cause. And it turns out a net force causes acceleration, not velocity, acceleration. And we can summarize this by saying that the net force equals the mass times acceleration. Mass is otherwise known as inertia, measures the resistance to motion that an object has. So take two objects, apply the same force to them. The bigger the mass, the smaller the acceleration. The bigger mass object resists accelerating more. Okay. In terms of units, the units of mass, we will use our kilograms, and we'll say that the units of force then, which would be a kilogram meter per second squared, and that's a mouthful. So we're going to define that to be a Newton. So a Newton is the name of the unit of force, and the symbol we'll use for that is a capital N. Okay. All right. So that's just a quick summary of what hopefully you remember from last Wednesday. In this video, what I want to do is discuss how to apply this idea to to a scenario where something's in free fall, and then maybe also work out a couple other examples. So the key thing that I want to show or kind of highlight is that we keep coming back to using this statement. Right? When we solve force problems, we come back to this equation over and over and over. So what we're going to do is come up with a process to help us systematically analyze situations. And the goal is to come up with an expression for the net force. Okay. So to do that, and we're going to pretty much always go about this the same way. So we're going to go through the following steps. Remember, I should also say, note, net means sum. And net force means sum. All right, so here are our steps. And it'll always be the same steps, so we should know it. Step one, list the relevant forces. So there are nuclear forces, there are other kinds of forces, but if they're not relevant to the dynamics that we're watching, then we don't bother. So for example, in this class, we'll never talk about nuclear forces. Okay. Step two is going to be to draw a free body diagram. Okay, I'll talk about what that is. It's basically a diagram of all the forces in the problem. It's kind of in the middle here. Maybe in parentheses, maybe step 2.5. Work out components if need be. Okay. Step 3, add. So add the forces to find F net. And step 4 is to take the output, whatever expression you have for the net force, and set it equal to ma. So use Newton's second law. Okay, so that is the basic process, and we will use it over and over and over. Really the same process for every scenario. Just got to be careful and work through all the relevant forces. So let's apply it to what arguably is maybe the most important force problem in this course. Or let's apply it to a free fall example. Okay. So in free fall, that means that only gravity is acting on an object. In particular, no wind resistance, no ropes, no pushes from a hand or a table or anything like that. Only gravity is acting. Okay. Note, in this situation, as we've talked about for months now, the acceleration is negative g pointing to the center of the earth. So we'll call that the y direction, but it should be to the center of the earth. All right. G, remember, g is positive 9.81 meters per second squared. All right. We know this, we've seen this by throwing things and shooting stuff across the room, whatever. All right. So in free fall, we only have to deal with gravity. So there's only one force, which makes it really easy to find the net force. All right, let's go through the process let's go through our problem solving process though, even though the answer is very simple. And what we will find is a formula for the force due to gravity, at least near the Earth's surface. All right, so step 1 for my process was to name the forces. Well, this one's easy. It's just gravity, which near the Earth's surface we call weight. If I say weight, I really am implying that we're working near to some planet or something like that. If we're way out in deep space, then I'll call it the force of gravity. Okay, so that's it. There's only one force, easy. Step 2 is to construct a free body diagram. Now, the way you do this is you draw, you represent the object. Usually I put in a dot, okay, just because it doesn't matter the shape. So I just make it a dot. And then I draw forces, and only forces, that act on my object. So in this case, there's only one force that acts on my object, gravity. Oh, all right. And I draw it with the arrow emanating out of the dot in the direction the force applies. So since the force of gravity acts downward, I put that arrow down from the dot. Some object, some mass m. And then I label this because W for weight. I label it, I mean, now it's kind of silly because there's just one force, so we know what we're doing. But when you have 5 forces or 6 forces or whatever, it gets to be confusing. So label everything, and you need as many labels as necessary so that it's all clear. Also, remember, every force gets its own arrow. Don't double up, because if you double up, you're sure to eventually just start forgetting stuff, and then it's wrong. Okay, so easy free body diagram. And now, I mean, truthfully, for this scenario, because it's so simple, maybe I didn't need that, but it's good to show the process. Step 3, work out an expression for the net force. Well, in this problem, there's only one force, and so the sum of one thing is just that one thing. So the net force is just the weight. And I can write that as, I could write it in components because there's only a y component. I could say the net force in the y direction is minus, sorry, take it back, is the weight in the y direction. All right, that's easy. If the weight had been diagonal for some, obviously not for a weight, but if the force had been in the diagonal direction, then you would have needed to found different x and y, maybe z components for everything. All right, but this one's pretty simple. All right, and then step 4 is to use F net equals ma. So here I have an object of mass m. I have an expression for my net force. I just plug everything in. I end up with net force being the weight in the y direction equals the mass of the object times the acceleration of the object. But since this is in free fall, we know that the acceleration in the y direction is minus g. And we know that every object has the same acceleration. And so the only, so then this formula for weight must be true for all objects. The only effect is this overall factor of mass. So we learn formula for the weight is minus mg, and it points to the center of the earth, which we'll call the y direction. That is one we should all remember. And that's true even if we add in extra forces. The weight is always given by this formula. So note what's interesting. Weight is not mass. So I say, oh, in class I'd say, oh, go weigh that mass. And then you tell me a number of kilograms or grams. So we're in everyday language, we are conflating things. Weight is a force. Mass is mass. It's a fundamental parameter, fundamental quantity. And near the surface of the earth, weight is proportional to mass. Or, well, weight is always proportional to mass, but up near the surface of the earth, that constant proportionality is just 9.81. And so it's trivial to go back and forth. And our balances, scales do that easily. It just automatically. However, in general, when you get out in deep space, this thing G isn't a constant. It's more complicated. And so the relationship between mass and weight can be more complicated. But conceptually, it's really important. Weight is not mass. Okay, that's really important. So if you were on another planet, the acceleration due to gravity might be different. So your weight, but your mass would stay the same. So you would have the same mass no matter where you are in the universe. But if you went to another planet, because G could change, your weight could possibly change. All right, so that's a really important thing. We've learned how to solve weight problems, or we've learned how to introduce the formula for weight, or to deduce the formula for weight based upon our other lines of reasoning. All right, next up, I'm going to do another problem. Remember, we talked about this. Normal forces are perpendicular to surfaces, and okay, and I would say anytime objects touch, assume there is a normal force. Right? Anytime objects touch, assume there's a normal force. If the math tells you it just happens to be 0, that's fine. But in general, if they touch, assume there's a normal force. All right. So the simplest example you might have would be the following situation. Imagine that there's a block on a table, resting on a table. Right? And since the table will be fixed, we'll just indicate that like so. Now, well, let's go ahead and say, you know what, just for convenience, let's say that the mass is 100 kilograms. So it's a heavy mass. All right. Now, I would like to know what is the normal force, the force perpendicular from the surface pushing up on the block. Okay. How would you do that? We'll go through our process. Step 1, find the forces. Well, there's a normal force and weight. Those are the only 2 relevant forces in this problem. Step 2, draw a free body diagram. Okay. So here's my mass. I have a weight going down, and I have a normal force going up. Step 3, express the net force. So watch how I do this. F net is equal to the sum of all forces. So I say what I mean. The sum. You might be saying, wait a minute, but the weight goes down. Why don't I subtract them? It's okay. The minus sign comes when we plug in the formula for weight. Right now, we just add it, whatever it is. That's what we mean by net force. Thing with minus signs is you don't want to overcook it. All right. So now I'm going to write this in component form. It's only in the y direction. And the normal force we get in the y direction, which is the only, that's kind of redundant because the normal force has to be perpendicular to the surface, which tells us it's in the y direction. And then the weight, we found from the previous example that the formula for weight in the y direction is minus mg and 0 in the x direction. Oh, I lost my place here. There we go. So that means that in this situation, I can substitute in for weight minus the mass times g, where the mass is going to be 100. grams or 100 kilograms. All right, and then step 4 says we use F net equal to MA. Now, this is where sometimes you have to find the acceleration. But in this situation, this is just an object sitting on a table. We know what the acceleration is going to be. 0, right? It just rests. So we know that the acceleration is going to be 0. So I can plug in everything I have for net force, use what I know about objects on tables, and I can solve for the normal force. So I have both the normal force in the y direction equals mg, because this term is 0. All right. So that's a pretty simple example where we use free body diagrams to solve for an unknown force. Let me do one more example. Let's just make up a problem. Let's just imagine we have a mass and there are 3 forces. Let's say there's a force going at 45 degrees and another one's going at straight down. And let's say this has a magnitude of 10 newtons. And let's say this has a magnitude of 5 newtons. Okay. Let's go through and let's assume that the mass is 1 kilogram. Let's go through this and figure out what the acceleration of this object would be. Okay, and I've already given you the free body diagram, but let's do one. Let's just try this. So I'm going to call this one force 1, and I'm going to call this one force 2. All right. So step 1, we're to label the forces. Just say F1, F2. I'm going to assume that gravity is negligible for this problem. Maybe it's out in outer space. All right. Step 3 is my free body diagram, or step 2 is my free body diagram. So that's just over here already. And now it's almost the same, but what really is the same as what we did before, but I have angles involved. And so I really need to kind of work out an intermediate question or problem, and that's to work out the components. So I have to work out the X and Y components of force 1. So force 1 in the X direction, well, in the X direction, I'm going to use the cosine of 45. So that's going to be 10 newtons times cosine 45 degrees. Cosine of 45 is 0.707. So this is going to be 7.07 newtons. And force 1 in the Y direction is going to be 10 newtons times the sine of 45. And because I chose 45 degrees, it's the same results. Okay. So that's kind of my side problem. Whenever you have forces at angles, then you have to do that little bit of arithmetic. Okay. So now I come back. After I write that out, I will draw my free body diagram. Then I write out step 3, which is to construct the net force, which tells me, so the net force is going to be the sum of these. So it's going to be force 1 plus force 2. I have to add them as vectors, which you always do in component form. So that means F net X is going to be force 1x plus force 2x. I go up here and I see that, oh, force 2 has no x component, only force 1 has an x component. So that's simply going to be 7.07 newtons. And I have to do the same thing for net force in the y direction. Force 1 has a y component, and force 2 also has a y component. So that becomes 7.07 minus 5 newtons, which would be 2.07 newtons. All right. And then the last thing is to use step 4 is to write F net, all this stuff, equal to the mass times acceleration, and then find the acceleration. And I told you that the mass was 1 kilogram. So I can write this out in the x direction to find 7. So let's look at the x. So the net force in the x direction equals mass times acceleration in the x direction. So I get 7.07 newtons equals 1 kilogram times the acceleration in the x direction. And I can solve for AX using the definition of Newton. You see that gives meters per second squared. And in the y direction, and I just write it all out. So I solve for AY equal to 2.07 meters per second squared. Okay, so those are a few very simple examples of how to use Newton's laws to analyze objects and forces and motions. So we'll do lots more and work with more and more complicated situations, but the basic process is always the same. Let's kind of summarize that. Step 1, identify the forces. Somewhere here I have it. Step 2, draw a free body diagram. Step 3, add the forces as vectors to find the net force. And step 4, use Newton's second law to solve for whatever you're trying to solve for. Okay, thank you.